All right. Hello, everyone. Yeah, the big moment is finally here. We are live with the reveal of the space engine and how everything works. We are today going to truly show everything. And I'm going to start with explaining a bit on how this is going to go down. And then we're going to go into the explanation. Gives people a bit of time to fill in as well. First, who are we? Well, my name's Kirian van Hest. This is my partner in crime, Thomas Fontaine. And our company, Kirian Technologies, has developed a engine that's capable of traveling through space. All the way to the stars. Because it allows for, well, it is an impulse engine, so it's not, technically speaking, continuous acceleration. But you can even it out across many impulses per second or per minute to get a figure for continuous acceleration. And thanks to space having nothing to slow you down, inertia allows you to basically add up every push you push in and just go faster each time. So today we're going to explain exactly how that works. We're going to go from simple to complex. So our objective is to explain it to as many people as possible so they can follow us along. Because we have many friends and family now who have been following me along for a long time on this ride. And I want to make sure they get as much as possible today because, well, they deserve it. First, we'll talk a bit about where we are with the company because people have been asking. We actually this week got a second rejection of the preliminary examination in which we are in after we changed from from function to form. So basically, we got rejected the first time because they said it goes against the laws of physics. It doesn't, but we are of the opinion they didn't give it a fair shake. However, we went with the very lawyer way of doing things, which is basically, okay, we'll take linear motion out and we'll just patent the design. And we just got the reply back that, nah, you're not allowed to do that either. So now we have no choice but to defend linear motion, and we are going to do that. We are going to show tonight that it does not break the laws of physics at all. I'm using them. But you can't just quote Newton's third law and ignore Newton's first and second law, and Einstein on top of that. We'll get into that, as I said. I also want to say up front that as to the accuracy of the math I'm going to talk about tonight, there's not going to be much, because this is supposed to be a presentation. We have multiple documents that will become available after the stream. Maybe not right away, we're still reading through them, but within the next week for sure. It will become available on our website for download. And if you want to comment as to the accuracy of the math, you can just pick out another document to go deeper into it. We will be releasing a quick guide, which will show the theory and what the materials are made out of in a quick sense, and give you, in fact, a quick and dirty way to build one of your own, very cheaply. Using just a bunch of PVC, really. So it's interesting for everyone to read, and it's written to that level. We will release a document that argues specifically against the comments of the first comments of the PCT search, where I will show that this is not a closed system, this does not break Newton, and I go through the entire cycle of the engine proper, using as advanced math and logical concepts as I can possibly show, to as well show that I am indeed skilled in the art. If you desire yet more, I will refer you to Thomas's document, which is, I think, 48 pages of handwritten math in the classical sense that incorporates as little assumptions as possible to get as accurate as possible with our level of knowledge and understanding, which is quite high because Thomas went to one of the best schools in France. And if that's not enough, well, we're hoping that some big-brained superstar out there can then still look at the math and do it at an even higher level. But considering the error margins we have, meaning that the amount of forward motion we can get per cycle versus how much we lose in inefficiencies, we're pretty confident that even a higher level of math will show that, no, this must still produce motion. The law of conservation of energy states that this must produce motion because we cannot explain where else the energy ends up as. It doesn't end up as a heat. It doesn't end up along chaotic vectors in unwanted directions. It must end up as linear motion. Now, just to start off with, I will show you the figures of the patent. Let's get to it. I'm sure you've all been waiting for this. How does this damn thing look? Well, first to show you that the patent does exist, here we have the patent filing on the patent of PCT's thing, and this is indeed how it looks like. Show you a bigger version in a moment. I will provide this link in the description of the video when we're done and in chat at the end of the stuff. It also shows my personal information, but I don't give a fuck anymore. Go look, because I'm sure I'm right. And this is how it actually looks. Now, I understand that this looks a bit chaotic. There's a lot of lines and numbers, and that's not, you know, people can get kind of spooked by that. So I have here in Paint a document that I made which will bring this back down to a symbol, to a diagram, which is much more explainable. And we'll go through the whole thing. But I just wanted to show the full thing, and I'll be making it understandable next. So, here we are. Oh, well, go to the top. I was showing this to Thomas earlier. This is the basic setup. It's a ball in a tube. And I honestly can't make it any simpler than that. I'm pretty sure that's going to make many people think, no. But I have to say yes. It turns out that if you do the math, the ball does make it through the corner of the tube, and it does provide forward motion. But let me show you in general sense how it works. And you're just going to have to believe me for the time being that what I'm saying is indeed true. And we will, as I show you here, go over the whole thing. There's plenty more to talk about today. So, in basic terms, what you have is a ball, coils, copper coils, basically, that attract the ball and accelerate it through the tube. The ball goes through the corner, like so. And on the other end is slowed down by this bit of copper tube. So it goes very fast like this, slows down here, goes slower in this bit, and when it makes it back to the copper coils, it speeds up again. Now, there's a few things that we have to handle. I'm skipping over a lot of things, and as I said before, we will get to it. But the first thing you will notice is something somebody already noticed that I talked to after the last reveal, and that is there's actually two tubes. Now, for the rest of the presentation, I will be talking about one tube and the forces on one tube specifically, because it simplifies things a bit. And it compacts the drawings because it's already quite a big picture. But with everything I say about a single tube, assume, and it is, that in a mirror tube, at the same time, the same thing happens in mirror configuration. So these two tubes and these two balls are exactly the same. They weigh the same. They have the same mass, same density, same materials. They are exactly the same in every single way. And when the balls together make it to the corner at the same time, one ball will be rolling upwards and one ball will be rolling downwards. And because they are rolling in opposite directions, at the same time, the forces that are exerted on the tube, like so, cancel each other out in some sense. So it leaves a backwards force still, but the force that's exerted like this is cancelled out, and therefore the tube does not start to spin. Because as the tube is pushing the ball around the corner, the ball is pushing the tube around the corner. But if two balls are pushing two tubes in opposite corners, or in opposite directions, around opposite corners, at least the sideways motions cancel each other out. There is no upwards and downwards interaction, at least there's nothing not meant to be in an idealized situation. Therefore, you can see this as purely backwards and forwards motion on one single tube. This is just to explain why in the rest of the explanations I am talking about one tube only, going straightward backwards and straight forwards without sideways motion. Of course there is sideways motion, but this is how it compensates for it. And I will even show you that if we go back to my website, or our website, that now this model of spacecraft makes a bit more sense. There's one tube on one side, one tube on the other side, and they are compensating for each other, providing forwards or backwards motion. So that is the gist of it. Before we go into the complex explanation of why this works, I want to show you something first. Because so far, I've been saying to my stream, my followers and everything, that a prototype doesn't exist. And that is true to an extent. But to make all this a bit more understandable, I want to show you my proof of concept that I built in 2019. And the reason why I don't call it a prototype is because if I were to launch it into space, it wouldn't exactly work, because you can fire it once and it'll work once and it's supposed to reset itself. But to do that, I have to shorten the copper tube on it, and I don't want to destroy, you know, the very first prototype that was ever made. So, this thing has been hiding under my bed for 5 years. And now maybe it looks a bit more understandable. Instead of copper tubes, of copper coils, which would be here, these things are two electromotors that shoot it away, just like one of those tennis ball or baseball training machines that shoot a ball at you so you can bat it away. And of course that creates recoil, which makes it go that direction. Now, the reason why we're talking about materials specifically is because of the first innovation that this machine has, which is a mechanical innovation. And it's quite interesting. So, the reason why this slows down, this might be your first question, why does the ball slow down because of this copper tube? Is because the ball that's in here, let's see if you can hear it. Not really. It's magnetic. So I've got another one of them, just here. And you can see, yep, magnetic ball. So, where is it? Oh, there it is. You can see. The ball that's in here is also magnetic. Now, if you drop this ball through this copper tube against gravity, just like that, it'll fall slower than you would expect. This is a common physics trick, and I'm not going to keep this up all the time because I've got long COVID and my arms will hurt like hell. The reason why a magnetic ball slows down if you drop it through a copper tube is because the electrons that are inside of the copper material itself are affected by moving magnetic fields. This is how all electricity on Earth is created. You shape the material into a wire, which means that the eddy currents can only go in one direction, one way or the other, and then you drag a magnet over them to force them down one direction, and that gives you electricity. If you have solid material, the electric currents can move in any direction they want because they are not restricted. Other than, of course, by the material itself. So this is supposed to be insulated, but it's already insulated by the air itself because air is an insulator. So, because the eddy currents have nowhere to go but must stay inside the material, they will flow in the opposite direction of the magnetic field falling through, but within the material. So this slows the ball down. However, that also transfers force to the tube. And I'll switch back to the document for a moment, because I'll show you this via a very simple physics explanation. If you suspend a copper tube from a scale and you calibrate the scale to include the copper tube, you will see that without a ball in it, it says 0 because the scale is calibrated to the weight of the tube. Now, if you drop a ball through it with a magnetic field that goes through the copper, and the copper slows the ball down, the scale will show you the weight of the ball to the efficiency of the magnetic transfer. So it will show you most of the weight of the ball, almost all of it, but not quite all of it, as it falls through. The moment the ball falls through the tube and the magnetic field no longer interacts with the tube, the weight of the ball disappears. Now, weight is just mass times Earth's gravity in acceleration. Therefore, if the tube carries the weight of the ball, there must be kinetic force transfer. Because otherwise the tube would slow the ball down, but it would not display the weight of the ball on the scale. Because there would not be any kinetic transfer. How can the tube carry the weight if it doesn't have to carry the weight? I mean, it wouldn't make sense. So, furthermore, there's a second experiment, both of these you can do at home, that shows you that if you send a ball at speed through copper, or a magnetic ball, it does push the copper forward. And we'll get to this in a moment when I explain how the full rotation actually works. But if you simply send a magnetic ball at speed, and I tested this, it was hard for me to do. So you need quite a bit of lung capacity, and you need to send the ball through its speed. So make sure you're aiming at something soft, because the ball will go through. But as the ball goes through, without touching the copper, which is on the outside of a PVC tube, the copper will still fall off the end of the tube. Now, that means there is kinetic force transfer into the tube, in the copper tube, as I said. So if in this situation you would glue the copper tube to the PVC tube so that they're attached, then it would feel as if the PVC plus copper tube were pulled from your hands as you blow the ball through, because there's kinetic force transfer. And the reason the tube falls off the PVC here is because it's not attached. If you attach it, the kinetic force can also transfer into the PVC, and the PVC would drop instead. And I've tested this in real life, so I know it works. No, so just to show off this little thingy again, because I'm proud of it. I'm not going to fire it because it makes a hell of a noise, plus it doesn't have the electromagnetic coils I would need to prove the full concept. But, interestingly, when I fired one of these balls through it, and it went through this corner, I didn't see any movements because this thing is way too heavy and this ball is way too light, and I didn't take any of it into account. I just had to get it out of my head. But this ball attached to this one right here. Yeah. So this is why I don't want to take it apart again, because I would basically have to saw off like this much copper and then reattach it, but then it would work. So I wanted to show that off. Because that thing has been hiding under my bed for a long time now. I haven't been able to talk about it at all, and this has been quite painful. Now, most of you will have the obvious question. Does the ball make it through the corner? Because I'm sure you're willing to believe me that if you fire a ball with a coil gun, which is essentially what we're doing, you get recoil. I'm sure you're willing to believe me that with a space engine in space, where there's no gravity and nothing to hold yourself onto, you get basically forward motion out of the recoil. There's nothing to stop the recoil, so you just move with the recoil. And I'm sure you're willing to believe me by now that if I shoot a magnetic ball through a copper tube at speed, it'll slow down because of eddy currents. This is well known within physics. That also means that there's force transfer to the kinetic tube, as I've shown and as you can test at home. So that means that the tube will also still go in that direction. But does the why does the copper tube speed the whole thing up instead of slow it down? It doesn't that go against Newton? We'll show you that it doesn't. And the second question is, does the ball make it around the corner, really? And the answer is yes, it does. And because the patent office has said that this wasn't written by somebody skilled in the arts, I am regrettably forced to become pedantic now and show you exactly that it all works. According to Newton, according to Einstein, according to all the classical laws. I'm not changing anything about physics here. And we're going to get into that now. So, to start off with, the reason why it works is because you have to take into account all the laws of Newton at the same time instead of just Newton's third law. So, as we know, Newton's third law is every action has an equal and opposite reaction. You can also rephrase it that if you've got two spheres of equal weight and mass in space, and they push on each other, or you input force, it doesn't really matter which one pushes on which one, because they push on each other. And because they are of equal mass, or equal weight, no matter how you want to see it, the numbers work out equally on both sides. So Newton's second law says acceleration equals force divided by mass. So if you want to know how fast something is accelerated, you take the amount of force you put in, you divide it by the mass the object has, and that gives you the acceleration you get. So if we input 20 Newton here, and it doesn't matter which one pushes on the other, that means that both of them get 10 Newton. And if we input 10 Newton divided by 1 kilogram, you get an acceleration of 10 meters per second squared. On the other side, you get exactly the same. So that lines up with what we observe in reality, that both spheres would move away from each other at equal speed. And the first second, they would have traveled 10 meters distance at 10 meters per second of speed. But because it's acceleration, if you keep inputting 20 newtons of force per second, then the second, it would have traveled 30 meters, and it's now going at 20 meters per second. And the third second, it would have traveled 60 meters, and now going at 30 meters per second. So every second you input 20 newtons of force between those two spheres, and if they can still exert it on each other, this is just what happens. And this is why we calculate it via acceleration, because we only need this formula instead of having to break it down into its components every damn time. This ends up being a lot of work, especially when the numbers start getting really big. Now, if we introduce Newton's second law and third law in an asymmetrical situation, the numbers change a little, but the formula doesn't change. And that's why the formula was such a genius invention at the time. If we make one object 10 times as heavy, or as massive, whichever one you prefer, as the other one, then you will see that the numbers still line up, because the 10 times as heavy object is accelerated 10 times as slow as the object that is 10 times lighter. Now the numbers still line up because you can just basically take off this 0 and you can see it's still the same. It's exactly the same thing. It still lines up because the force is equally divided between both components. Equal action and reaction. But you simply cannot ignore Newton's second law when you say that something goes against Newton's third law. And you will probably agree with me, as I just shown in the physical model, that it is very likely that the tube attached to the copper coils, attached to a frame, will be heavier than the ball itself. This is also a requirement in the patent. It's one of the very few musts of the patent, is that the tube assembly is always heavier than the balls. Because if the balls are heavier than the tube, the ball can spin the corner in the tube instead of the corner spinning the ball, and then you end up with some really weird results. So that is a requirement, but it's hopefully an obvious requirement. Something I neglected to mention earlier because it was obvious to me, I'm sorry, is that the material components here are very specific. So because the ball is a permanent magnet, the tube material itself is non-magnetic. PVC is just the simplest to imagine for people at home, but wood, polymers, probably carbon fiber, anything you can roll a magnet through and it doesn't meet any physical resistance, that's what you want for tube material. The coils, of course, are just copper wire, or anything that you can make an electromagnetic coil out of. That should be well known. And this is just a solid copper tube, but you can also use aluminium. The most important thing is that you use paramagnetic material. That means aluminium or copper, really. Paramagnetic material generates an electrical magnetic counterfield whenever moving magnetic fields move through it, such as a permanently magnetic ball. That's why you have paramagnetic material here, and that's why this is called the paramagnetic brake. This also means that the force we use for braking is basically the same force that we put in there at the beginning, because energy is conserved. We'll get to that as well. Now, the numbers I will be using for the tube and the ball will be similar to this to keep everything simple. And we'll get to the drive pattern now. This is what you've all been waiting for. These are the figures I'm using. You can see that the tube's corner has a radius of 1 meter. So it's basically 1/2 of a perfect circle that is 2 meters in diameter. The other half would be, the other corner. The total tube weight of all its connected parts is 10 kilogram. At this point, we're going to ignore some things. We're going to assume some things to make the calculation simpler and not to be caught here in a discussion that is 16 hours long. Again, if the accuracy is not to your liking, we will refer you to the math document that will be released in the coming week, which is, again, 48 pages of very classical math that takes everything into account, and it still says everything works. So this is a simplification in the end, even though it's already pretty complex, and you will see that soon enough. So the circle radius is 1 meter. The coils collectively consume at least 20 joules of energy to produce 20 newtons of force. We have to talk about this right now because it goes to the conservation of energy, which I've also been accused of not adhering to. So first off, you can use multiple coils to accelerate a ball and then basically add all the acceleration up for the entire segment. Because the ball starts with 0 speed and it leaves it at x speed, which gives you a total of acceleration across this distance for, a certain amount of energy. So if it bothers you that it's not one coil, but it's 3 coils, it's just to show that it's additive, but you can also just use 1 coil for the calculations if you feel more comfortable with that. Now, for the conservation of energy, I'm using newtons of force, but I'm always using more than 20 joules of energy. Thanks to the International Standard System of Measurements, we know that 1 newton is effectively 1 joule. So 1 newton of force is 1 joule of energy, and you can just convert that directly, which is nice and convenient. So we know that in the most idealized situation possible, which we will never get in reality, you will have to still use 20 joules of energy to get 20 newtons of force. It will forever be impossible to get 20 newtons of force here with 19 joules of energy. That is absolutely impossible. The law of conservation of energy forbids it. However, above 20 newtons, above 20 joules, I can use whatever number I want. So if you're telling me that, well, of course, you only get the maximum amount of force transfer if the electromagnetic fields are near each other's center, because magnets are very strong when they're close by, but they're weak when they're further away. This is fine by me. That just means that when the ball is further from the center of the coil, you have to input more energy to get a certain amount of newtons of acceleration. How much more energy? Go wild. Take 100 joules. If this thing is 20% efficient overall, and I'm only using a 20 newtons of force input, well, 20% is 5 times less than 100%. So we just do 20 joules times 5, and you get 100 joules of energy. So if you need to input 100 joules of energy to make 20 newtons of force work in this setup, do it. Take 200. Why not? It's on sale. That is why the law of conservation of energy will be conserved in this device, because I don't specify how much electricity I'm actually going to need to generate this amount of force in the situation where the tube is 10 kilograms and the ball is 1 kilograms. I don't know, and we'll find out once we start building these things to actually go somewhere in space. It also means that probably our limitation here is going to be the amount of electricity we can provide to the engine to make it run, rather than material strength or anything like that, at least for the first generation. All of that is well and good. I'm willing to accept that, but none of it means that this can't work. So again, whenever you see newtons of force at the beginning, just remember, whatever more than 20 joules I need, I'm taking. But at a minimum, you need 20, and because of conversion losses, you will need more. Because, some of the electricity doesn't turn into an electromagnetic field. It gets lost as heat thanks to the resistance of the copper, which is an inefficiency. Thus, you need more than 20 joules of energy. Simple as that. Now, one more thing that's obvious here, that might be, but not so obvious right away, is this guy down here. My little stationary, non-interactive third-party observer. This guy is effectively Einstein. Well, he is there because of Einstein. It's not because Einstein told him to be there, but because everything is relative. And that is also one of the reasons why you can't simply just quote Newton's third law and say this goes against it. This guy represents somebody or something, camera, astronaut, doesn't matter, that is looking at the starting position of the ball in the tube, as it is right here, and this guy does not move. He does also not interact with the ball or the tube. Not via gravity, not via electromagnetism, not via radiation, no way. He's just floating in space having a good time, watching all of this go down. Now, as far as the... no. We'll start with the explanation of the first phase, and everything else will fall into place from that point onwards. We'll go to the first phase, acceleration. Thanks to Newton's third law, and there nothing being in space to hold you onto, once you let electricity flow through a copper coil, it generates an electromagnetic field. If you have a permanently magnetic projectile, it also works on non-magnetic ferromagnetic projectiles to be specific, but then the magnetic field has to be in range of the material itself. With a magnetic ball, it only needs to be in range of the permanently magnetic field of the ball itself, because the magnetic fields both interact. Now you can see that here. Well, I've drawn a representation of it. Remember, representation, I'm being conservative with everything. All of this is compressed and all that. So we turn the electricity on. It creates an electromagnetic field. And when the ball is in the middle of the electromagnetic coil, the coil turns off. That way the ball is only accelerated in one direction and not decelerated in the other. And then we turn the next coil on so that it continues to accelerate. We do that with the third coil as well, every time providing an input to the other direction. Now we all know that if you shoot the ball down the tube moves in the other direction. Question is how much? Since we've defined the tube as being 10 kilograms of weight, and we've shown earlier that there is a mirror setup doing everything at the same time in the opposite direction, so there are no sideways forces here, the balls will be accelerated down the tube and the tube goes in the other direction via this calculation. Now, we state that this goes down in 1 second because it makes the calculations easier, but the difference will still be there if you take more than 1 second to accelerate the whole thing to this speed. Really, it doesn't really matter. It just means that if you want to get a 1 kilogram ball up to a speed of 10 meters per second, you're always going to have to input at least 10 newtons of force. Because that is what the law of conservation of energy states. The energy isn't generated, it is transformed. It is conserved. Now, of course, this doesn't take heat losses into account, but we've taken that into account with the more than 20 joules of energy. So we can just look at the force. And the force is, well, converted by nature, so it must be perfectly conserved. So what you end up with after the phase of acceleration is that the ball is going through this thing and ends up here and is now moving at 10 meters per second in this little section where there is no interaction between the ball and the tube. That is vital to understand here. The ball and the tube are not connected. That means that this is not a closed system. It might seem like that because the tube encloses the ball, because the tube is around the ball. And indeed, in reality, there is a negligible amount of gravitational attraction between the ball and the tube because both have mass, and mass attracts each other across the galaxy. However, that attraction is incredibly tiny compared to the amount of electromagnetic force we just put into it. So you can basically ignore it. And without that tiny attraction, this thing imagining floating in deep space, let's say it's in the middle between the Andromeda and the Milky Way galaxies. So there really is no gravity to speak of. There is there's a bit of radiation, but you can kind of ignore that as well. Because, that is way less than 10 joules of energy per second, or anything like that. So really, the ball and tube do not interact if there is no force whatsoever. And that is incredibly important to understand. Because we'll see that in the corner, which is the phase 2. Because obviously, it makes it to the corner. And the ball does interact with the corner when it's touching the corner, but it only interacts via the force transfer. So basically put, this would answer the question of if you have action and reaction, and you've got this straight tube, and you put a ball in it, like so. Yeah. And then the ball pushes the tube, and the tube pushes the ball. The ball goes like this, and the tube goes in the other direction. But then the ball comes to this part here. And now the ball hits the side of the tube. And the tube pushes back in the other direction. So basically, the tube moves sort of a distance this way. And then here it stops again. Now, if the tube and the ball are equally heavy, the tube and the ball will move an equal distance. If the tube is 10 times as heavy as the ball will move 10 times as far as the tube, but they will still come to a stop. However, you can see here with the corner that there is no blockage for the ball. From the perspective of the ball, there is nothing in the way until the side of the ball hits the corner, because that will happen before the middle of the ball hits the corner. This means the ball being a ball and rolling in the inside of a tube, it will roll. Now, the reason it rolls around the corner of the tube is because the tube is 10 times heavier than the ball in this example. So if you throw a ball into a curved tube here on Earth, it makes it through the corner, no problem. Everybody will accept that, because everybody thinks that the tube is stationary. Technically speaking, it isn't. It's being pushed back a tiny little bit, but because the Earth is so incredibly heavy and the tube being connected to the Earth, it basically doesn't move. Now, you can reduce that, like say, okay, let's say the Earth was the moon. Let's say you have a smaller planet. Well, the tube still doesn't move. If you toss like a baseball in it, like the baseball is so light compared to the moon, well, just reduce that concept even further. You go from the moon to an asteroid. You go from an asteroid to a really large spaceship. You go from a really large spaceship to a tiny spaceship. And at some point, you just reduce it to being only 10 times as heavy. So if the ball is 1 kilogram and the tube is 10 kilograms, then the ball has 10 times more difficulty moving the tube than the tube has moving the ball. And because there is a difference there, the tube wins. It's basically the ball can't move the tube out of the way fast enough to continue its linear journey or just deflect from it. The tube is too heavy and it's moving forward. That means, thanks to friction between the tube surface and the ball surface, is that the ball will start rolling. If it starts rolling, it doesn't lose any speed, because it can just continue to roll around the corner. And in space, there's nothing to slow you down, and since there's nothing in front of the ball, there's only the side of the wall to the side of the ball, it actually does not slow down. It just continues to go onwards. The only question is, how much does it push the side of the tube backwards? Because the side of the tube is connected to the rest of the tube. You know, the knee bone is connected to the head bone. So if the side is being pushed back, the entire thing has to be pushed back. The ball makes it through without pushing the tube back entirely. And the reason for that is it is moving at 10 meters per second. And we've defined the radius of the tube as 1 meter. If you find out what the actual length, the circumference, so I'm taking the outer path here, what that is of a meter, of a circle with a 1 meter radius, and then you take half of it because it's only half a corner, you end up with 3.14 meters. Yes, pi is involved. Now I'm hungry. But that's why you end up with 3.14 meters. Now, logic simply says that if you have a ball that's going at 10 meters per second, and it has to travel a path that is 3.14 meters long before it reaches the other end of the corner, it only has 0.314 seconds before the ball is even through the whole thing. Because it's 3.14 divided by 10. So you get 0.314 seconds before the ball's through the corner. So the ball and the tube still exert the same force that we gave him in the beginning, because energy is conserved. In the beginning, we gave them acceleration through the consumption of electricity. That was the force of acceleration. Here, there is no force of acceleration. The ball and the tube are not attached. So they can only interact via the vector of force transfer, which is the side of the tube. And now you gotta understand something, that just to show how complex this can get, there is a difference between whether the ball is connected to the tube or not. Because if we just take the center of the circle, which is about, let's say here. We draw a line to the ball. Let's say that this is connected. And we rotate it along the pivot. So the ball comes here, it connects to an arm, and then it stays connected to the arm to the entire corner until it leaves here. You can see, along with the arrow, that there's a constant force pulling the ball back on the tube because, well, it's attached. But if it's not attached, then how can the ball exert any other force on the tube but from the point of contact? And again, because we have a mirror setup, all the force that's going in this direction, because the arrow is slanted, is compensated for, and you only have this force left. But it's not that much. It's not as much as you would expect because some of the force is compensated for. But anyway, as the ball is rolling around the tube, by the time you get to the halfway point, something happens. So now the ball is trying to do this. The tube is still moving forwards, but the ball still doesn't win the pushing match, so it continues to roll. Now when it's... well, take it here, it's even more obvious. When the ball is going in this direction now, because the curve, the side of the tube has turned a linear vector around the direction, how can it exert force like this? The simple answer is, it cannot. It's going in this direction, but the tube is still deflecting it. So that means the force must look like this. It's now pushing in this direction. But remember, on the other side, there's a mirror setup with a ball doing exactly the same thing in this direction. So at this point in rotation, the forces are completely compensated for. Basically, the tube does not move. It can't move, because the only force acting upon it is pointing upwards, and there's a other force pointing downwards compensating for it. So the force of a ball rotating through a disconnected ball, sliding along the side of a tube, that generates different forces than a ball connected to the center of a tube and moving along that pivot. I just wanted to mention a difference, because despite of that, the force calculations I'm using here are basically as if the ball was attached to the center. Again, if you want the higher accuracy version, I will refer you to Thomas's math document and have fun with that, because it still says I'm right. Anyway. Just to, well, the numbers are a bit different, but they're still positive. Just to go back to the math here, the amount of speed, forward motion, forward momentum, that's lost by the tube in this corner is about 3.14 meters per second. Out of the 1 meters per second, it was already going forward. But you have to understand, by the time the ball reaches this position, the tube itself is also moving forward with 1 meters per second. So you have to take 0.314 meters per second off of 1 meters per second and not 0, because the tube itself is moving. So at the end of the first cornering phase, the ball will be located in front of the brake. The tube will be going forward at 0.686 meters per second. And the ball itself is now also moving forward at 10 meters per second. Because the ball has not lost any speed in rotation. And we're taking the rosy view here because it compresses the amount of math we need to do. Makes it a bit more understandable. Again, we have documents that have more specific data. Now, the stationary observer still hasn't moved. And as you can see, it wasn't looking at the coils before, but it is now. And that represents the amount of distance the tube moved during cornering and before the ball reaches the corner. Now phase 3 is where the ball makes it through the paramagnetic material. And this is the phase that confuses physicists. I'm speaking from experience here. That has already happened. So I've drawn it all out to show you in a very simple manner that yes, you can accelerate the ball and the tube down here with electromagnetism and then slow the ball down on the other side, and it will speed the tube up instead of slowing it down. If this seems confusing, you can think about it very simply as such. If you throw a ball, you get pushed backwards because of the recoil. So if you have to brace yourself. You think about standing up straight, holding a 5 kilogram exercise ball. Those things are pretty heavy for a human to hold. So if you then push that ball away from you as hard as you can, you know you're going to fall over backwards. However, if you just stand still in the same position and somebody throws that ball at you, everybody also knows they get pushed backwards. Now, those are two impulses in the same direction, and how can that be? Well, because in the first situation, your relative speed to the ball is 0, because you're holding it. And the ball's moving as fast as you are. That means, according to Newton's first law of inertia, you have to input force to change its state. You know, object at rest stays at rest, so you have to input force to bring it to motion. In the second position, and you catch the ball has a higher relative speed than you, so it has a higher relative force than you. And you catching it is equalizing that force with you, meaning the ball brings you up to its speed. Now, the ball being lighter than you, if you brace yourself, you can, avoid falling over backwards. But in space, there's nothing to hold you back. So, the only question really was, does it make it through the corner of the tube? And I show here, and in many documents, that it indeed does make it through the corner of the tube without pushing the tube backwards with minus 1 meter per second. Because that's what you need to get to here in order to break this. You need to achieve minus 1 meter per second by the ball in the corner. It doesn't. The tube is still going forwards when the ball leaves the corner of the tube. So, when it goes through the paramagnetic material, the ball will be traveling faster than the tube itself. Simply because the ball didn't lose speed thanks to rolling. And the tube went at a speed of 0.686 meters per second, with the ball going 10 meters per second, which is obviously higher than the other one, meaning that the ball will travel forwards faster than the tube does. Which means that the tube now is basically like a cowboy on a horse trying to grab a moving train that is the ball. The cowboy is sped up. Now, the ball is light here, so the ball is slowed down by the tube as the tube is sped up by the ball. Because it's the tube catching the ball. And we're still not inputting any force here in addition to the original electrical energy right here. The electrical energy was consumed. Either a battery was drained or we captured some solar rays that were produced by fuel being consumed inside of the sun. And that's it. We didn't electromagnetically interact, or we didn't consume any other electricity than that. So the ball still has the force we inputted into it originally, which it preserved through turning linear motion into angular motion, meaning it started to roll. And the tube still has this much force of the original put into it. So if the tube slows the ball down by 5 meters per second, and the tube is 10 times as heavy as the ball, then the tube speeds up by 0.5 meters per second. It doesn't even matter anymore how speedy this transfer is. You can make a very long, very thin paramagnetic tube, and then the ball slows down slower than if you just make a thick brick. But in the end, if you take off 5 meters per second of speed of the ball, that energy has to go somewhere, and if it's the tube slowing the damn thing down, it is the tube that speeds up. So at the end of phase 3, as you can see here, the tube will be traveling at 1.186 meters per second, and the ball will be traveling at 5 meters per second of forward speed. And this is the part where it gets difficult. If you lost it already, boy oh boy, is the next phase really gonna hurt your brain. Because we have to leave Newton behind. See, even our stationary observer gets it. If the tube catches a faster detached object, the tube speeds up via action-reaction rather than slowing down via action-reaction. He gets it. But in phase 4, we have to incorporate Einstein as well instead of Newton. Because now, and our calculations show this, the ball does make it through the corner, the ball does make it through the break, and it does transfer force. But now the ball is going to make it through the second corner, and the tube is no longer stationary. Because the tube is moving to the left here at 1.186 meters per second. The ball is moving in the same direction at 5 meters per second. So the only force you can transfer into the side of the tube in the second corner is the relative force and not the objective force. It's like pushing against the inside of a train. You're not pushing against the ground on the outside, you're just pushing against the train. Now, since the ball is going 5 meters per second, and the tube is going 1.186 meters per second, the actual force being exerted on the corner of the tube is equal to 3.814 meters per second. So, since the tube is still 10 times as heavy as the ball, it adds 0.3814 meters per second to the tube, but it only does so for the time that the ball can exert its force against the corner of the tube. And now a little bit of magic happens. The travel path of the corner of the tube is still exactly as long as the first corner, because both corners are identical to each other. So the ball still has to travel 3.14 meters. However, because in this phase we took off 5 newtons of force, we also took off 5 meters per second of speed, which means that, thanks to the relativity taking off even more speed, the ball is now moving relative to the inside of the tube, the surface of the tube, by 3.814 meters per second. So it makes it through a path of 3.14 meters in 0.823 seconds. There's a lot of decimal points here, so I'm rounding to 3. The funny thing is, if you do this number, 3.814 meters per second times 0.823 seconds, so the speed the ball has versus the time it has to go through, that comes down to 0.314 meters per second. And if you add that number to the speed that the tube already had, then by the time the ball makes it through and it ends up on this side, essentially going backwards again at 5 meters per second, because the rolling means it doesn't lose any speed, the tube is going forwards at 1.5 meters per second. Now, we have an advanced document written by me. It's not the most advanced math we have, but it's the in between a quick guide and Thomas's math huge document. I've got two numbers here with a lot of decimal points, and I times them together and I end up with 1.5. Like, it is insane how I can't make any of this up. As long as you assume relativity, so you take into account the relative speed differential against the tube, the math just lines up. So, there is one more phase, technically speaking, and that is the next phase. We've gone through, let me just say the names. We've gone through the acceleration phase, when the ball and the tube both picked up speed thanks to the consumption of electricity. We've gone through the cornering phase, when the ball takes off some forward speed of the tube, which is what you pay to realign the linear vector of the tube, of the ball, I mean. Basically, you lose speed of the tube to turn the ball around. Then you've got the force transfer phase in phase 3. This is also why it's called a force redirection electric engine, because you consume electricity in the beginning, then you redirect the force in the corner, and then you take it away. And because of the redirection, the ball now going in the opposite direction of before, you can add the force to the tube instead of subtract it. Again, via equal action and reaction, because the tube's 10 times heavy, and it slows down it speeds up 10 times less than you slow the ball down. You slow the ball down by 5 meters per second, and you speed the tube up with 0.5 meters per second. All according to Newton's first, second, and third laws. And then you incorporate Einstein to make sure that the force transfer in the second corner when both objects are moving in the same direction lines up. And you end up with the tube being 1.5 meters per second going to the left and the ball going 5 meters per second to the right. And because the ball is going less than 10 meters per second, which was the number that you ended up with after the first acceleration, you can input more energy. Again, energy is conserved because I'm using more than 10 joules. So whatever energy you input in the first calculation, input half now. The energy is still split across two objects equally via Newton's third law, which means that the ball, being 1 kilogram, will be sped up by 5 meters per second over 1 second, let's say, makes it easy, which adds to the 5 meters per second it already had, which means it again ends up with 2 meters per second for the ball. Meanwhile, because the force is equally divided, 5 Newton also goes into the 10 kilogram tube, which speeds it up by another 0.5 meters per second, which adds to the 1.5 meters per second it already had, which gives you 2 meters per second. Which shows that just according to the laws of Newton, it speeds up more. Why? Because you turn the ball around twice. First, the ball and the tube move in opposite directions, and when you convert the speed, they move in the same direction. So the only question you have is, does it make it through the corner without pushing it back completely, like Newton's third law by itself would say? And I've shown many times that it does not. And it still means that energy is conserved because, let's say Our stationary observer, which still hasn't moved and is now looking at the last coil. Like, you can actually see this. If we draw a line through it, it goes through the center of his face on all of them. So he hasn't moved. But he started looking at the ball from its start. And now he's looking at the last. This is not to scale. I don't know if that would actually move that much. It's just to indicate that the whole device is moved, while somebody who didn't interact with anything hasn't. The guy that's still located at the starting point is still there. Now, if the worst comes to happen, and this ball is over here, hang on, it's right here, and this guy has a brother, which is unfortunately, oh wait, his brother's standing here, with the tube heading in this direction. Hang on. Naturally, that's not going to be well for, going to end up well for him, unfortunately. But, you know, sacrifices are needed. What is the force that this thing impacts him with? And the answer is very simple. Because we added up plus more than 20 joules of energy with more than 10 joules of energy to get 30 newtons of force in total, of which now 20 newtons is in the tube because it's 10 kilograms of mass going at 2 meters per second, and 10 newtons is in the ball because it's still 1 kilogram, but it's still going at 10 meters per second after the second acceleration. Then when this whole thing crashes into his face, he's going to experience 30 newtons worth of force. Now that is instant transfer, of course. The force transfer happens over time, and if you want to go through the difficulty of actually calculating all that, be my guest. But I'm telling you, you can't get more than 30 newtons out of force with somebody who was stationary compared to the beginning, because you never input anything more. Where's the force supposed to come from? So in that way, energy is conserved. It must be conserved. And as such, this device must work. This must be an engine. Because we can get it to move in one direction and we can get it to accelerate in that direction. Now, of course, if you were to try and do this on Earth, there's a little bit of a problem because gravity's pulling you down, which makes for a lot of friction. And the initial design of this will not produce a lot of forward thrust compared to, say, a rocket. So you wouldn't get a lot of motion and the atmosphere slows you down. So it's kind of a problem testing this thing on Earth, I think. But I think it could also pretty much be done very easily, because if you have a PVC tube, if you have a magnetic ball, if you have a couple of electrical copper wires and a bit of copper tubing with the right diameter and everything, and you could build two of them that are exactly the same, synchronize them, you have yourself a space engine. Well, we have the application filing for it now, so we have ourselves a space engine. However, I've been talking for about an hour, and I think that's more than enough to go into this amount of complexity, because if anybody wants to, they can look for the patent itself, which contains, this is an English version as well, but it contains the figures, the description, the claim. Side's a bit wonky. Now it wants to know if I'm not an AI. Great. Yeah, that's right. You get it. We'll update the link and everything there. Oh, hang on. There we go. We're back to our faces. But that's basically it. Again, I've gone through it on pretty surface level. I still need to do a final read of the documents that we're planning to release. I'll send them over to our webmaster Vanya as soon as possible, and he will update our website when this stream has been turned into a video, which I hope people will share then. among friends, among family, because you never know who everybody's connected to. You never know if they know somebody smart who looks at the math and say, "Oh shit, this is real," because we know it's real. I've gone through it with all of my logic and capability, and I've not been able to break it. Even going through all of it again with a second reply of the PCT office this week and preparing for this presentation, I still can't see why it doesn't work. Not from a logical perspective, not from the math that I can do, and Thomas is certainly convinced that it does work. So I'll ask him to talk a bit about it now, since we planned for me to do most of the presentation. But of course, it's his device now too, since we're doing this together.
Well, as Kirian has said, I spent a bit of time writing a math document just to apply what I've learned over the years in physics and confirm or disprove whatever we thought and discussed with Kirian. So number one, I argued with Kirian for a long time on details. And when that engine goes into development and production, engineers are going to literally scrutinize every single piece of this engine and come up with much more complex systems, equations, and testing devices and improvements and optimizations. But my goal was to just verify every step, every stage, every different phase, as we call them, of the engine, and literally write down the equations from Newton's magnetic also science. I actually went into the last knowledge in this area just to, take some assumptions on numbers and verify, with a little bit more precision what I was getting into. But, at the end of the math is one thing, it's really first and foremost applying the laws of physics that does matter. In this case, it's actually a very simple engine. The math gets rapidly more complex. That's why eventually mathematicians created different ways of handling Newton equations, and it became Laplace and Lagrange and so on, and basically allowed more advanced physics and theoretical physics. But this engine can be calculated in simple Newton laws, of course, with the relativistic point of view in memory and in the behind of the whole thing. But it's really four phases. I've applied reasonable assumptions to my math in terms of permeability, magnetic susceptibility, mass, dimensions, of course, without taking into account friction and heat and other small losses of energy. It's really about conservation of energy, of basically of quantity of movement, and the right applying of vectorial, math and solving these equations. So it can get a little bit complex in the end to get to final results. It's really a sequence at the end of the day, if you think about it mathematically. Of course, it's a theoretical model. In practice, it's going to be a little bit, going to have to be more refined, but it does work. So I come up with different results from Kirian on the numbers. Why? Because it's a more practical case that I wrote at the end. So I wrote every phase. I applied the equations of the laws of physics, try to solve each phase in mathematical terms, and then just put the whole thing together in a few rounds, basically with numbers that mimic some realistic assumptions of a practical case. And basically, it continues to accelerate round after round after round. It's I would not say continuous acceleration. It's just continuous acceleration in terms of the fact that it actually continuously accelerates round after round after round. And it's been done with state of the art, So, it is written by hand because I had to actually do the calculation, and it took a little while. I'm sure we're going to improve that document so it is a bit more readable in the future with, a normal Word or PDF document and more polished graphs but that's the way I've learned physics. So at the end of the day, it was much easier for me to do it by hand, so I could calculate the math and come up with the ideas to simplify the math. But at the end of the day, I think Kirian has done a very good job at explaining it simply. It is a simple thing. Actually, it's as simple as possible. Let's put it that way. That's a good sign, by the way. And let's never forget we are in space, in microgravity, right? So literally these two, that's the genius of the engine, is that these two elements are actually separate, right? They're separate, but they're staying within the same range of speed at all times, right? So they literally cause an impulse at every single round on one, that causes the tube to go forward. It's an asymmetrical system, as he described, because it pushes twice. I think he does a very good explanation, also explaining it with a ball. Maybe you can do that later, Kirian, if you want, but it's on the website. But at the end of the day, it's really that simple. And I think it works. It does work. And so my math is, the results I get are a little bit more extreme than Kirian. The ball is slowing even more for me, but it's still sufficient to get back into phase one, get reaccelerated, and so on.
Well, we can show that now. So on our website, you can see how it works. We gave an example of a guy pushing a ball away and being compensated for completely via action and reaction. And the second example, being an asymmetrical situation, is where the guy pushes it off center and the ball rotates because it's attached to the guy, but because the guy is heavier, the ball stays within its range and kind of just starts to orbit around him. And if I bring up the PCT figure now, I think a lot more people will get the example now, because instead of a guy throwing the ball away, you have electromagnetism pulling the ball forward, which naturally means it pulls backwards on whatever the electromagnetism is attached to. And what you have to realize is that if you have insulated wires, the electricity is basically caught within the wire. Even if the electrons in the wire are attracted by the magnetic field of the ball, they cannot move past the insulation of the wire. So they basically push against its side. So if you're ever wondering where is the physical connection coming from that is affecting this force transfer, well, it is the electrons that are trapped by the insulation material in the wire and in the permanently magnetic field of the ball. It is the spin of the electrons of the atoms and molecules that is oriented in the same direction. And because a spinning electron still counts as a moving electron, it generates a tiny electromagnetic field. And as long as all those tiny electromagnetic fields are pointed in the same direction, we observe it at our size. And you have a permanent magnet, as we understand them. Now, what I want to do is just show the math that Thomas made. Just quickly, I'm not going to go into it, but I wanted you to just see that we do have just pages and pages and pages. I'm about a quarter way now. So, formulas, equations, assumptions, everything written out, whatever you want, it's there. And we will be putting this on the website for you to enjoy and for you to argue with. So this is also the point where we basically say, bring it on, scientists. We're about as sure of our case as we're ever going to be without outside help. And if we're right, remember, every cycle is additive. You might not realize this, but at 10 meters per second squared of acceleration, which is not going to be the first generation, but we're going to work up to it, you can overcome Earth gravity, because this thing, even though we've been describing it in microgravity, thrust is thrust. You know, there's only 9.81 meters per second squared of acceleration on Earth, and you fire a ball at 100 meters per second, it's going to do a full rotation in less than a second. So it's more than enough to compensate for Earth gravity. If we can get a future design strong enough, not only will it compensate for Earth gravity, but 10 meters per second squared of continuous acceleration is going to get you to 50% the speed of light in 6 months. You need to understand that that is so fast, we cannot reach this speed within the solar system. The solar system has a speed limit, which is way lower, simply because it takes you 6 months to accelerate up to 50% the speed of light, and light passes our solar system in, I think, 16 hours, end to end. So, after 6 months, you have 32 hours to slow down, or you're going to overshoot our solar system. That's the kind of speeds we're talking about here. At that speed, it takes you 6 months to accelerate up to 50% the speed of light, 8 years to travel, take or give, or 8.5 years, and 6 months to slow down again, which is a total of 9.5 years, and you're at Alpha Centauri, the nearest solar system. And this is the point where I talk fantastical, because all of these things are real. They're just simple physics. We can build a Dyson sphere with this concept. Now, probably not us, not our generation. No. It's going to take a few hundred years to generate enough space infrastructure to make something like that. But the concept is simple. If you have an electrical engine that can output a constant amount of force, well, at a certain orbit around the sun, there's a certain amount of gravitational pull. So, at a certain orbit, there is a constant 10 meters per second squared of acceleration directly downwards into the sun. If at that orbit, you just build suspension bridges with, hidden in the pillars, engines that can push the entire bridge up by 10 meters per second squared, it's effectively weightless. Because yes, there's gravitational pull, but there's also a continuous force that counteracts that pull. And once you have the continuous force, the suspension bridge itself only needs to carry as much weight as it does here on Earth. Because the road surface is being accelerated towards the sun at 10 meters per second squared from a stationary perspective. So it's like Earth. So all you do is you build a ring of suspension bridges around the sun with these engines hidden in the pillars, permanently giving away thrust, and you don't need the structure to hold itself up with material strength. You just need the suspension bridge to hold itself up. And you just keep building those rings, you connect them with plates, and you can have these engines pull them up as well as push them down, or, push them up. And you get yourself a Dyson sphere. Yes, the material requirements for that are enormous. That's why I'm not saying it's going to happen any century soon. But the theory is sound. Rather than creating a shell of high strength material that compensates for that attraction force itself, you just output force via some of the electricity you absorb from taking the energy from the sun to begin with, because that's why you build a Dyson sphere. There's other things that this technology will make you understand, like the most optimum shape of a spacecraft. It's just an apartment building. Why? Because the opposite floor of whatever you attach the engines to is going to be the floor. So if the engines are attached to the bottom of an apartment building, your floor stays your floor. You attach them to the side, and your wall becomes your floor as your engines push you sideways. Therefore, all the sci-fi ships are wrong, or they're explaining away the difference using some nonsense sci-fi method, such as Star Trek's inertial dampeners. Well, the reason the sci-fi shows all make ships look like seafaring ships is because that's what we're used to. But the actual logical best shape for any spaceship is an apartment building, and you move up and down with ladders. Because the moment you have 10 meters per second squared of acceleration, you effectively have Earth gravity, and your ship needs to withstand Earth gravity. Basically, the best way to build a ship is to stack it on top of its engines on Earth, and if it doesn't blow up or doesn't crumple, it holds itself up in space under 10 meters per second squared of acceleration. Because that's acceleration. That's continuous acceleration. That's a whole different ballgame than rockets, which use a lot of acceleration at the beginning and then use inertia to just coast. And I know that this can bring us up to the speed of light because rockets don't use exponentially more fuel to go to the moon. Most of the fuel rockets use is used to get up into space. But let's say they're in a stable orbit now. Then the next meter per second they accelerate is not exponentially less than the meter after that. You know, it doesn't go 1, 2, 4, 18, 200. It doesn't go up exponentially like that. It goes up exponentially according to the speed of light because it happens via time dilation. So the reason why it doesn't cost way more fuel to go to the moon for a rocket is because it never moves that fast to really affect time dilation. But at 50% the speed of light, you have 15% time dilation. So time is moving 15% slower. How this translates to my engine will immediately show you that this doesn't break any laws of physics, now that you know that it's just a ball in a tube. If we configure the engine to give 10 impulses per second in our time frame, at 0 meters per second, basically, then it will always give 10 impulses per second because it's configured to be this way. Now, if we accelerate that engine, or we let it accelerate up to 50% the speed of light, where there's 15% time dilation, what we stationary people will observe is 8.5 impulses per second. But anybody standing on top of this engine, thus they accelerate with it, and they themselves are now 15% time dilated, they will observe the engine to do 10 impulses per second. Because the engine and them and their perspective are time dilated. So if those people looking at the engine who see 10 impulses per second then look outside to the stationary people, they will see them move slower by 15%. Because the people on board are time dilated. Meanwhile, the stationary people observing the people being time dilated will see everybody move 15% slower on the ship. Oh wait, it's faster outside, slower inside, yes. So as the people on the ship observe the world passing them by in fast forward, the people in the world observe the people on the ship moving in slow motion. That is time dilation. And if you think this through, you go to 99% the speed of light, and let's say there's 100 times time dilation, so everything at 99% the speed of light moves 100 times faster than in our time, 100 times slower than our time frame, then 10 impulses per second becomes 0.1 impulses per second. Meaning, it now takes you 10 seconds to get one impulse. And suddenly it makes sense why it's going to take you forever to actually accelerate to the speed of light. And this thing does not break any kind of Newton or Einstein laws, even up to the speed of light. Can this thing break the speed of light? I will never know. Because if it's capable of that, it does so at the end of time. Because as you approach the speed of light, the time outside speeds up so fast that by the time you hit that last meter per second of acceleration, billions of years are passing in a nanosecond, and there will be nobody left to tell your observation to. So does it break the speed of light or not? We will never know. But I assume not. I assume there's just some kind of turbulence around the speed of light that will break the whole thing apart before it can accelerate faster. But we'll find that out, actually. And this device also allows us to start screwing around with time. Because we've never had anything that we could bring up to such a high speed that we could start experimenting with time dilation. We've measured it in reality. NASA sent 3 satellites up in different orbits, but the same speed, then brought them back down and measured very precise atomic clocks on board of the spacecraft, together with an atomic clock that was synchronized but had never brought up the speed. And they found that all 3 satellites had atomic clocks that were behind the clock on Earth. So we know time dilation is real, and we can even measure it. But because of the speeds we're working with, we need extremely precise measuring equipment such as atomic clocks to even see a difference. Once we bring one of my engines up to the speed of 50% the speed of light, and there's 15% time dilation, we can just observe differences. It'll be very simple. We just put a bunch of material on board, we send it off, we bring it back, and we see how much it's aged. And if any of it has aged less or more than we expected, according to time dilation, we have a winner. You can start screwing around with it, and it's only a matter of time before we start breaking time travel. We don't actually need to break the speed of light. We need to break the speed of time. Because it's not space slowing us down, it's time dilation that's slowing us down. It doesn't matter what source of energy input you use, thanks to time dilation, it takes you so much more time to actually input the force into reality that you can't make it to the speed of light. That's why it costs infinite energy. So I think that's... I kind of already forgotten how we got here. But I guess I just wanted to show off. Like, I've had quite a few revelations working on this technology. And I'm just very happy to start sharing them now. No longer need to think about keeping quiet and just throw it all out there. We are protected under the PCT filing. And we can copy that date onto national filings when all that is said and done. But it's no sense waiting for the legal process anymore, keeping the secret, because too many people are skittish without knowing how it works. We've had some interest, but that's all. They don't want to go for this unless they get all the goods. Even when we offer to send them the goods if they show serious interest, but they're not serious. So, yeah. We're just going to go with everything out in the open now. And see where it leads us.
We have a cool question, Kirian, on what happens if the system is shaken by external impact, like a little push from an asteroid.
Yes, let's get to Q&A. If you have any questions left, or if anybody dares ask a question. I'm much more friendly than I look like. Trust me. I'm more than happy to answer. So, what happens if the system is shaken by an external impact? Well, we actually had a discussion about this earlier. Is difficulty goes up exponentially. Thomas doesn't like me to use the word exponentially here because it might not actually be exponential. But because the ball in the tube is disconnected, if an asteroid pushes the tube itself, that might or might not affect the ball. Because if the ball is traveling sideways like this, and you get a little bit of a push backwards to the tube like this, then the tube is accelerated forward. But it's going along the exact same direction as the ball is. So since the ball is going faster than the tube is pushed a little bit faster, well then the relative energy between the tube and the ball decreases. The tube because the speed is increased. So if the tube is going 1 meters per second and the ball is going 10 meters per second, you have a relative difference of 9 meters per second. And then you push the tube with 2 meters per second via an asteroid or something. So you add 1 plus 2, that equals 3 meters per second. But the ball is disconnected and it's going in the same direction. So it's 10 minus 3 is 7 meters per second, which means that the relative energy differential is now also 7 newtons. So let's say the ball hits the inside of the tube somewhere later on. Before the asteroid impact, it could transfer 9 newtons because the speed differential was 9 meters per second. After the asteroid impact, it can only impact with 7 newtons because the speed differential is 7 meters per second. And this is all completely regardless of what the speed of the ball in the tube were before any of this, because just think about something in orbit. The International Space Station orbits at a height of about 400 kilometers upwards. At that height, there's actually still 90% of surface gravity left. So the gravitational attraction in the International Space Station is about 8.9 meters per second, more or less, squared. Yet the astronauts are weightless. How is that? It's simply because in orbit, you're actually falling towards the planet continuously, but you have such a forward speed that you just miss the planet. You're just really bad at aiming. And with enough speed, you miss the planet so consistently that you have a circular orbit. Now, if you bring two objects to the same speed, they will still have the same circular orbit. And that's basically what the International Space Station is. It has a shell, an atmosphere, and an astronaut all brought up to the same relative speed, so they appear weightless. But they're all just falling at the exact same speed under the exact same force of gravity. So with an International Space Station, the same thing. If a small asteroid impacts it and it doesn't destroy it, it will push the entire station to the side, and anybody stuck inside of it will just get smacked. That's a real danger. You know, astronauts can really get hurt from that. If they would ever get hit. That's why the International Space Station has engines that move out of the way for debris if they detect it. And, it's actually funny, those engines are Russian. And because of current climate, the Russians don't want to replace those engines when they're done replacing. So, how's the space station going to move out of the way if the Russians don't maintain the engines anymore? Our engines could replace theirs. Purely on the basis of electricity, because the International Space Station already has solar panels, so you don't even need to bring fuel up anymore. That is the true... Well, I've said it a couple times now, but one of the genius parts of this engine is that it generates its own fuel in space, because its fuel is electricity. Because the force transfer comes from moving that electricity through copper wires, which generates a field of electromagnetic attraction, which attracts a mass, and because it attracts the mass, itself is also attracted by that mass, and thus both things move towards each other. And therefore the recoil gives you linear motion in space. I think that just completes the argument in the circle. If something can work at macro scales, the chances it works at micro scales, moreover, totally solid state, are pretty decent. And that's another thing. This thing is scalable. Now that I've explained how it works, people should be able to see that it's just scalable. It doesn't really matter if your magnetic ball is this big or this big. The forces still work the same. As long as you go bigger than quantum mechanical effects. So if you have a collection of about 1,000 neodymium atoms that have been magnetized to have their spin all in the same direction, I think that would constitute enough to have no quantum mechanical effects on the entire object itself, as long as it's being, quote-unquote, observed in reality. But it's still neodymium atoms. Those atoms still have electrons, and those electrons can still be spun in the same direction if you put enough current through it for a short enough time. Basically make a magnet out of it. So, practically speaking, I would expect this engine to come in variants from matchbox size to car size. If anybody's ever seen those giant diesel engines they use on cruise ships, this thing can just be just as big. I mean, of course, the power requirements are going to be massive if you want to move a giant ball quickly. But even if you don't move it quickly, it still transfers the force. It still moves. You know, a metric ton, a ball that's worth a metric ton, doesn't have to move fast in order to transfer a lot of force. So there is this thing where if you go bigger with the engine, the ride gets more uncomfortable because you get bigger impulses spaced further apart. And that's not going to be very comfortable to anybody riding that without any shock absorbing. You know, if we build a giant freighter like that, we can have the ore move back and forth. That's not much of a problem. But we would need to make a cabin for any crew that compensates for it and smooths out the movements back and forth over time somehow. Otherwise, they're going to get seasick. But on the other hand, if you configure the engine to just push a lot of balls very quickly, it should start to feel as vibrations at some point. Because you're just getting a lot of these pushes against the surface. So if it's just fast enough and you have a battery of engines working asynchronously, it does increase complexity, but it can also work. It should be possible even to transport humans with this concept. Totally. And there's something I haven't shown yet. I'll show you this. Obviously, if one ball works, multi-ball will also work. And here we have a paramagnetic brake that is configurable. So rather than use a copper tube around a PVC tube, of course you can also just use copper material that you can move in and out of range of the tube. Therefore, because magnets only work really well in the short range, you can configure how much force is actually transferred. And naturally, if you're going to stack a lot of these engines of a big size, you're going to need something to hold those engines. There's two ways to do it. A block frame, which is just a server rack. Literally just a server rack. That's why I haven't even put it into the patent, because a server rack will be the optimum size and shape to just create motion. But if you send very big balls at a decent speed through a bunch of copper material, it's going to generate a very strong counter field very quickly, which means it'll be big. Basically, it's an EMP. And you might want that EMP to be away from other engines, because that EMP will attract other magnetic objects within its range. So, figure 7 here is a star core. I've called it a star core, because why not? Basically, engines are slotted into a frame, 2 at a time. So the forces are directed into the center of the frame, or away from the center of the frame, which means that the center of mass is in the center of the frame, the whole thing will go straight. And when the ball goes through the paramagnetic material on the outside, it can create a magnetic flash up to about like this big. Like quite big. And the longer the engine is, the bigger that range gets, without affecting anything else. Now the accelerator units are close together, true, but as long as the balls don't touch each other, or the magnetic field of the balls don't touch each other, and the accelerators are many tiny ones, like I've shown here, many tiny accelerators instead of one big one, you get a small electrical field for a long period of time down here. So if it's small for a long time, it's less likely to reach into the other tube and disturb the other tube. So that's why it's on the inside. But you can't really do anything about the EMP you create on the outside. So that's why I've done this setup, where you can't just have... you don't just have 2 engines compensating for each other, but you can have pairs of 2 engines compensating for each other, and you can just have a whole bunch of them. This is also kind of important for, commercially interested parties, because our design lends itself extremely well to mass production, to the point where, you're using 2 exactly the same engine cores to compensate for each other to form one full engine. That means you're going to have to make a lot of them according to exact specifications. And a lot of production means a lot of sales. A lot of sales means a lot of money. It's just that simple. You're not looking to sell just 2 engine cores. You're looking to sell a battery of 50 of them just to go forward. If you want to have a cube in space that can move in any direction, has all directions of freedom, you're going to need at least 12 of my engine cores to make it do that. But at the same time, they can make it do that. They can make the object strafe, they can make it rotate, they can make it go forward in any direction, backwards in any direction. You would get exactly, basically sci-fi spaceship amounts of movement, using only electricity, but still using electricity. So it's not a perpetuum mobile. It doesn't break the laws of conservation of energy. I'll just say it again just to make sure everybody gets it. It's real. Yeah, another question. How much energy is needed to move a spaceship of 10 tons, for example? Still a huge nuclear reactor? Yeah, that's where we go into the long periods of how much we will actually need. So I wouldn't expect the first generation to push a 10-ton ship. After a couple of upgrades, second and third generation, it's more likely. It's not entirely impossible, but we don't exactly know how much energy that will take. Regardless, yeah?
Well, I think it's 1 or 2 degrees of magnitude higher than needed a large nuclear reactor, right? I've taken 550 kilojoules of energy in my case for a 100 kilogram ship and 10 kilogram ball. So we are probably 1 or 2 degrees of magnitude, but it's true that if the ball continues to, you have to provide constantly. So I think we are 1 or 2 degrees of magnitude higher than needed here.
That's true. But at the same time, it is also true that I don't see a future for space infrastructure if we can't get regular nuclear reactors working in space. That's what we're going to end up with anyway. Because whatever math we throw at it, one thing is absolutely certain. To get 1 meters per second for a 10 kilogram object, together with 10 meters per second for a 1 kilogram object, via 20 newtons of force, you need at all times at least 20 joules of energy. So how much energy we will actually need, we don't know. We will find out. But we already know for sure, for certain, that it cannot be less than 20 joules for 20 newtons of force. So it's just an efficiency problem. For instance, if you use one giant electromagnet instead of many different coils and then you add it up, it takes a long time before the magnetic ball reaches the center of the electromagnet, because it has to travel quite a distance along a big one. That also means that your optimum force transfer, which happens close to the center, cannot happen for a very long time. Which naturally means that your engine is going to be very inefficient. It still works, it's just very inefficient. And the way you can see it is, let's say you have a waterfall, and the water's already falling because of gravity, and then you put a turbine in the way. But if you then pull the turbine out, it's not like the waterfall gains more energy or loses more energy or changes anything about its energy state. It's merely that you didn't tap into that energy before, then you tapped into that energy, and then you didn't tap into that energy again. If you send electrical energy through copper coils, you create an electromagnetic field. Sometimes this isn't even desirable, because if you send a lot of power through a copper wire, such as with a rail gun, forces that we won't even deal with, then the wires leading to the rail gun start attracting anything metal. I've seen this from people who send a large amount of current through copper plate trying to melt it. At some point, the wires they were using to feed the connector started attracting each other every time you fired it, because the electromagnetic fields became so big. So, if we want the wire to not have that field, because we don't want it to interfere with anything while we need a lot of power for it, it's actually a problem and not a boon. Like, it's something that's there that we don't want to be there, but we just have to deal with. But in space, you create an electromagnetic field in space, and you don't have it attract the ball, because the ball is like plastic, so the magnetic field goes through it without doing anything. You're just wasting energy. I mean, the energy is conserved because you did make an electromagnetic field at a space-time point in time. So you used it, it was used, it was turned to electromagnetic radiation, and that's it. Energy conserved. There you go. But if you then put a ball in the way that is capable of interacting with electromagnetic fields, such as a permanently magnetic ball or a ferromagnetic ball, and it then gets attracted, then you're just tapping into energy that was previously not tapped into, but still used. Because the question of whether electrons move through a copper wire or not is answered by the resistance of the copper wire. As long as the amount of power offered is more than the resistance of the wire, the electrons will move and electricity will move. This happens regardless of what you do with that force generated. So we are totally free to tap into it and have it move a piece of mass. How much that is moved? Well, we have math to tell us that. In an ideal case, 20 joules gives you 20 newtons. But because the magnet will never be near the center of the coil when it starts accelerating, it's never an ideal case, and you need more than 20 joules, but you can still get 20 newtons. So there's enough force to move an additional mass except the... Damn, the chat scrolled. So there's enough force to move an additional mass except the mass of the engines then? Yeah, totally. I just showed it. It's because in space you have nothing to hold on to. So the ship will always move. It's just a question of how much. Because I can change the calculation again easily. Instead of a 1 kilogram ball and a 10 kilogram tube, I'll take a 100 kilogram tube and a 1 kilogram ball. Because then the ball will still be accelerated to 10 meters per second squared, or 10 meters per second via 10 meters per second squared for 1 second. That doesn't change because we haven't changed anything but the ball. We haven't changed anything about action and reaction. But if the ship's, or the tube, 100 kilogram, then it's 10 divided by 100, 10 newtons divided by 100 kilogram, which leaves you 0.1. And if you do that for a second, you get 0.1 meters per second. We can increase it to a metric ton. That's 1,000 kilograms. Then you get 0.01 meters per second. You can increase it to 10 tons. And you will get 0.0001 meters per second squared out of a 1 kilogram ball. But that's just not very useful, is it? You're not going to go anywhere very fast with 0.0001 meters per second. Even if you accelerate it, it's going to take you decades to approach like 1% the speed of light. So how do you solve that? You just get a bigger ball. A 10-ton craft, 100 kilogram ball. But then 10 newtons is going to make that 100 kilogram ball move at 0.1 meters per second. And at 0.1 meters per second, it's going to take an age to get through the corner. All that time it's pushing back against the corner, so it is pushing the whole assembly back. But the whole point of it is that after one rotation, you might still be going at 0.1 meters per second or something for the tube, which is quite a bit for a 10-ton craft. But to get one cycle, you have to wait 10 years. There's nothing in life that's free, my friend. So if you don't want to wait 10 years, you just input more force. How do you input more force? You use more joules. So you just dump more power into it. Can I get a million metric tons of spacecraft moving using just 1 metric ton balls? Yes, I can. But that's going to require 2 nuclear reactors. If you want to have any other power on the ship for stuff like life support. It seems kind of important in space. But it can be done. The theory says it's totally possible. Einstein and Newton have already done the work for me, mostly. This thing will just scale. That's the beauty of formulas. They scale. That's hard. Can you create a Rosen bridge? I don't know what that is.
It's a wormhole.
Oh,
yeah.
No. We're not that level of technology. No, this will not go faster than the speed of light. This will not break any laws. This will not create wormholes. This is not sci-fi, which is why it's so exciting. Like, people should be excited for it. This is real life sci-fi. You know what the best plan is that NASA has to get us to Alpha Centauri? It's this giant solar sail that's going to take 37 years to get there for a planet 4.26 light years away. And very likely it's not going to be able to decelerate once it gets there. You know what my engine does? Within 1 year, if I can get 1 meters per second squared, 1 meters per second squared of acceleration, you go to 50% the speed of light in 5 years. 1 meters per second acceleration, and I can show you a picture of the planets of Alpha Centauri, including the time it takes for light to travel back to us, in about 22 years, and probably within 20. That's how big a deal this is. Now, of course, that assumes the ship is built. But taking development time and costs into account as well, for 100 million, I can probably get you pictures of Alpha Centauri in 25 to 30 years. 100 million is, by the way, the difference between a communication satellite, which is 200 million, and a military communication satellite, which is 300 million. Just to put things in perspective. I'm excited. Well, good. So, well, we've been going for a while, and the video will be long enough now. For any additional contact, there's a contact form on our website, KirianTechnologies.com, or Kirian.tech, which also redirects here. You have this contact form for serious talks about, commercializing this, getting a license. We will update the How It Works page with the video and the documents as soon as possible. That will happen within a week for sure. This is the next thing we're going to work on. And the link will be included in the things as well. Hang on. Just get it again. There. I'll post it in chat right now. Oh. There it is. If that doesn't work, search for EP 2022 /076767. All of this will be updated in the description in the future as well. So if you can't find it within the next day or two, check back in a few days and it'll all be here. Just to show that it is all real. None of this is nonsense. It's not a reactionless drive, okay? It's not an EM drive. It's not one of those weird things. I'm not claiming any laws of physics that have changed. I haven't even redefined any of it. Technically speaking, I could redefine action-reaction into the equal division of energy, and that's just a semantics thing. But other than that, it's classical. It's to me it's obvious even that this works. I have a heck of a time understanding why other people don't understand it. I mean, sure, I had to think about it, but it took me 5 minutes. So if people don't believe us after today, well, I guess that's just our battle to fight then again. That's always, it's always hard to believe something revolutionary is possible. But it is. I can even say that even if this design wouldn't work, which the math says it does, but even if it doesn't, I can change things around a little bit, add a few more coils, change the positioning of the objects I already have, and I can guarantee it this will work. But you slow the ball down in the corner. You do it twice at the same time in a mirror configuration, it compensates for each other. So then you waste force. It's not as efficient because you waste force, but the balls will guarantee you slow down without moving the thing. It for sure works. It has to work. It has to work. This is the hill I've decided to die on. I'm gonna make it work, even if it doesn't. But I'm sure it does. Amounts of current development. I don't know what you're saying here.
P's and P is a software theory thing. We're not in software theory here, it's physics.
Yeah, it's pure physics. It's something physical. In fact, the Kirian Technologies is going to focus on physical analog devices just like this because I am convinced there's a massive gap in the market for analog devices. Simply because our development as a human society over the past 20, 30 years has been, how do we make this better? Can we put a computer in it? That's basically been it. And because of that, I think there's just more ways to apply the laws of physics we already have with our current day understanding of them. And come up with devices as this. So, yeah. I missed the first and the second half of the show. Can we get a quick synopsis? No, there is no quick summarizing this. This entire video is the summarization of the math document I showed earlier. That is going to take you a couple of days to just read, let alone work through. We have a quick guide that's like, I don't know, 12,000 words. Show that off for a second, why not? So it contains the overview of operation, which goes through the theory in a very compressed manner. And then we go through the specifics of the design, well, what material you need to use where. And then at the bottom, I use a quick build prototype where you can build your own. PVC tubing, neodymium magnetic ball, copper aluminum tube. It's pretty simple stuff, really. If you're wondering why I haven't built it, is because Thomas is stuck in France because that was required. He needed to have a job to immigrate back to France. So he's transitioning his obligations now to the next layer. He's the main value out of their company. He can't just up and leave in that case. But he will be helping me soon. And me, with my long COVID, I've been just physically deteriorating. Where the last project I work on, which was something different, because I need to keep making innovations now, I had to saw some tubes, and I could do that, and now I can't anymore. Because sometimes I have difficulty walking just visiting my dad. So physically, I'm just done. And I need a company. And one of the reasons we're going public now is just to attract more attention and get that ball rolling. It's simple as that. If somebody else on YouTube builds it and verifies it before we do, that's no problem with me. It just means we go viral faster. Yeah, because people will know that it works. They will believe their eyes. And it will be independent verification. Although I'll say, when I asked Thomas to do the math, I told him, this is the best I can do. I just gave him examples of math. But I am not sure, because math is not my strong suit. Logic is. And via logical exclusion, all of this makes sense. But I don't know how everybody else has defined it in which way, because I'm also autistic, so I come to different conclusions. And Thomas has done the work completely independently in that way. Still came up to the answer that it has to work. So he already serves as verification for my work. I don't really get why people need more. Maybe because he has a monetary interest in it, and that's not enough because people aren't allowed to earn money earnestly these days. We have to start a crypto scam, and then it's okay. You know, we're trying to do this the correct way and not scam anyone, because we're not scammers. We're legit. We're actually legit. And I understand that this is in a sector where these kinds of scams are rife. That's why we're being careful about it. That's why we've taken a long time. That's why we've prepared all these documents. Because we're not scammers. This is actually something that works. Just believe us, please. 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 Oh, just look at the data. Just look at the data. That's all I ask. And if you can't break it, if you cannot prove that this does not work, if you can't disprove us, just be honest about it. Just be excited about it. It's a whole new day for humanity. We're going to travel to the stars. But don't hide it because you're jealous because somebody without the right credentials managed to come up with a good idea. You know? That just breaks my heart every time. We've already encountered that, and I'm sure we'll encounter it more. I was prepared from it from the beginning, and I will fight it to the end. As I said, this is the hill I decided to die on. But just fuck, if you can't disprove it, just be honest about it. Say, okay, I can't disprove it. Maybe somebody better can. Even if you don't want to believe it. But that's my challenge to other people who are smart enough to understand Thomas's documents. Go disprove it. And if you can't, just be honest. Best of luck. Thank you, Loki. And thank you, Sergey, for asking all these questions. Lots of more people without creds coming. Yeah. Well, we'll see if we'll get anywhere, but I hope so, because unlike we're not going to hide anything anymore. We don't have any need to be hiding our math. And the moment we get our company started, we are planning a visit for Thomas to the Netherlands. We'll get a location, get some stuff. Hopefully, we'll look at personnel, but we can build a prototype between the two of us.
The company exists, the site exists, the LinkedIn page exists, and I'm going to focus professionally on this. So it's a different ballgame now.
So there you go. Also, they say, you know, extraordinary things require extraordinary proof. That's why we've just been careful about it. You know, we could have presented this 4 years ago now. Or I could have just presented it the moment I invented it. Just given it away. But outside of the fact that I wouldn't be able to patent it then because we're on a first to file system instead of a first to invent system. Meaning that if somebody else files first, we're screwed. We have the filing now. But, yeah, now it's just getting the company started. And understanding the whole thing better, of course. But after all this time, I still can't find a way in which this doesn't work. If you don't assume anything, and if you do the work yourself, I can't find why it doesn't work. I'm asking if anybody else out there can find why this doesn't work. Because if they cannot find why it doesn't work, the logical conclusion is, it must work. And it'd be a real drag to me if we cannot do this intellectually, and I have to build a prototype before anybody will believe it. Because if we become that stupid that we can't even discuss things anymore, we can't even gain knowledge through communication, we have to be a bunch of cavemen about it and show it in reality. I swear to God, I am going to ask a lot of money whoever comes to me after that. Then I'm just pissed off. You know? All I want to do is something good for humanity. But if I have to beat it into humanity with a stick, well, then it's going to cost a price. That's my pain, my effort, my worries, my stress, my finances that I have to work with then. And if I have to go through all of that alone, or well, me and Thomas, the rest is just going to pay if we make it to the end. Question is, can anybody afford for this not to work? Question is, anybody out there interested in this, can you really afford to wait in case it does work? And give everybody else an advantage. Understand this. Every company out there in the world has already wasted 6 months of secrecy. If they had just approached us, took a license 6 months ago, they could have developed this over the next 6 months. They could have already had a head start on everyone for 6 months. And nobody gives a shit because nobody cares about expediency anymore. Well, fine. Now you get to compete with everyone. And I'm sure there's going to be lots of companies that are going to be skittish and they don't want to approach us because they don't trust it. Fine. Fine. You know when you're going to enter the market? When we already have people who've entered the market. And then you can compete with them. You don't have to compete with us. We don't even want to focus on production. I want to focus on creating the next generation of space engine and get people to the stars as fast as possible. So if we can focus on licensing out architecture and just focus on the architecture, that's what I want to do. But if I'm forced to go to production, not only is it going to take longer, by the time I win, I'm not going to sell to Microsoft or Amazon or Google or anything. I'm going to keep everything for myself.
As you know, Kirian, these companies are already knee deep or neck deep into their own shit. So they don't have time to look for breakthrough ideas yet from outside.
Yeah.
We have to make it obvious.
This invention is the only thing that's going to make Starlink profitable. Because it allows Elon to stop sending up more ships every 5 to 7 years. Because the one thing that's limiting Starlink now is the onboard fuel. Starlink is orbiting at such a low height that the atmospheric drag it experiences is so high they have to consume fuel to keep their orbit. After 5 to 7 years, that fuel's just gone. And the whole thing burns up in the atmosphere. With our device, they can generate the fuel in space with the solar panel they already have. It can stay up there forever. Which means that, well, of course you have material wear and tear, but it'll be much less than just running out of fuel. So let's say every satellite doesn't last 5 years, it lasts 20 years. Which means that instead of shooting up a new one every 5 years, which you have to do 4 times in total to get to 20, you can shoot up one and it'll last 20 years. Which saves you 3 launches of rockets. And the most expensive part of the whole system, getting it into space, is getting it into space. It's the rocket launch. So not only is this going to make Starlink profitable, this is going to make every other constellation out there profitable. Because without this, the replacement launches just don't make it worth it. So if Elon doesn't contact us, or doesn't want this tech, just sell it to somebody else. And by the time he starts losing money in the market, he'll come to us. But then he has to compete from a disadvantage. As does anybody else who waits. I don't know if anybody's seen the movie Margin Call, but it's pretty simple. There's 3 ways to make money in the business. Be first, be smarter, or cheat. I don't believe in cheating, because we're legit. I think we've got the smarter part covered. So that just leaves be first. And it is as simple as that. It doesn't matter to me who is first. We have to patent to the technology itself. We'll get a percentage on the entire market, no matter who wins. So good luck. To anybody out there with money, just good luck. We'll take it how it comes. Of course, if you think in terms of a nuclear reactor, once we get that going, the rock will glow for a certain amount of time in space, which means it'll give off a certain amount of power for that time. The half-life of plutonium is 82.3 years. So if you have enough plutonium to give you a kilowatt, after 82 years, you have 500 watts left. You have rocks that are radioactive for longer, but they also give off less power per second, as you might imagine. However, if you just use enough of the material, you can have one of these things accelerate for 1,000 years if you want. Because that's the beauty of electricity as a universal fuel. We've already figured out how to generate electricity for a long, long, long time. So it's only a question of how do we use it to create linear motion. And we have. To make it a bit easier to think about, just think of a torque wheel. You know, if a spaceship has a torque wheel, which is just a big, massive wheel that the spaceship spins up, as the spaceship is spinning up the torque wheel is spinning up the spaceship, and that's how you rotate the spaceship. Well, you slow it down, and the spaceship slows down. Why can't we do that with a linear ball? Why can't we do that in linear motion? It's just a question of how do we get that pattern to work. And that's basically it. I think I found the pattern that works. Just what somebody had the idea of a torque wheel one day. That didn't exist in nature before. Well, maybe it didn't. Maybe they saw it somewhere, but they had the idea of if we bring a massive thing up to rotational speed, whatever we use to rotate it also starts rotating. Oh, so we can turn things in space using electricity. Yeah, you can rotate things in space using electricity. Just bring the wheel up to speed and slow it down again. I just found a way to incorporate that pattern in a linear fashion so we can get forward motion out of it. It's not any different. You have to understand angular momentum doesn't even exist. It's just inertia off center. If you're traveling forward and this is my center, then, that is just linear motion. And if there's a force pushing me like this on the side, I start to rotate because it's off my center. And that's all that angular momentum is. It's rotation, it's momentum around the center. So it's perfectly possible to just get linear motion out of electricity. Totally. It's just a matter of finding out how, and we found out how. Space elevator minus the infrastructure at 10 meters per second squared? Yeah, basically. Although you could make a space elevator out of this as well. Because if the engine can do 10 meters per second squared and still carry a bit of weight, then you just put the engine at like 10 kilometers up or 20 kilometers up or 30 kilometers up, no matter how big or small your section is. You have a section of 500 meters, you just have an engine every 500 meters. You feed it via a ground cable, because the whole thing is a space elevator, so just connect it, so you can use ground electricity rather than solar panels. And you just have the engine put out continuous force against gravity to get your space elevator. You don't need like a tether in space or a counterweight. I mean, it'll help, I think. But using my engine along sections of the elevator means that there isn't much structural force. Rather than the superstructure holding the whole thing up from the bottom, it's every section's being held up by individual engines, or, well, clusters of engines. So, in effect, a 500-meter section of space elevator is weightless. And I do mean weightless. I do mean you fire up these engines full blast, and you could just pick the entire section of the space elevator up with your hand, or pull it down. It would effectively be buoyant in air. Because the amount of force you're exerting towards the bottom to keep it buoyant is the exact amount of force you need. How do you do that? You consume electricity to do it with our engines. So you could build a space elevator with this, totally. Well, it's just going to take another 50 years for people to stop laughing at it, but theoretically it can be done. It can be done. Alright, well, I think we should end the video just about here, because we've shown off enough. Again, go to Kirian.tech or KirianTechnologies.com on how it works. We will update this as soon as possible. We will turn this into a YouTube video, as you can see here. I will add it into the description there. The link to the patent, which is also in chat. We're going to get everything ready for public release and update everybody on Twitter. We're going to spread the information as far as we can. We didn't do it up front because, honestly, this reveal is just for the people that watch us, that follow us already, or me and like my work. As a thank you for my followers that, yeah, you guys got us here. I would not have met Thomas if I did not have at least a decent follower base to attract enough attention to get interviews on YouTube. Everything leads to something. I don't know if it's causality or destiny, but it's all led to today, and I could not have done it without you guys. And now we see how much the world is interested in intergalactic travel. Don't be bearish on computers if you intend to coordinate an impulse engine. Yeah, look, eventually, space navigation is hard. But that doesn't change anything about the physics of the engine. And it just means that we are about to create a vibrant industry of companies specializing in navigation in space and making it easier. Navigational computers, navigational arrays. You know, a spaceship in Star Trek isn't just made out of the engines. A lot of equipment goes into that. And while it's pretty easy to make a drone to go explore the asteroid belt so we can get resource exploration going virtually immediately, to get humans to the asteroid belt, well, you need a life support system. I mean, we could get humans to the asteroid belt, but if they're dead, there's not much point, is there? So you need a life support system. As for pointing that damn thing, it doesn't really matter. I mean, there's asteroid belt in every direction we travel. I mean, aside from up and down, but we can visually eyeball that. You know, it's gonna take a lot of work. We're gonna make eventually some company out there is gonna make an enterprise computer, like the main computer of the enterprise, because it would require ever more computing power to push ever more complex craft ever faster in space. Of course, I'm not bearish on computers. I'm just saying that we've gotten a little away with ourselves and we've ignored the analog world too much. And we're going to try and change that. Alright, well, this is where we're going to end the stream. We're going to go to the ending screen now. I've said everything enough. Thanks everybody for watching, for being here during the big reveal. Thanks for family, for supporting us, and friends as well. Personally, I'll talk to my friends, see if anybody's interested in interviews. I will do my regular streams on Twitch on Thursdays and Saturdays. Feel free to come and ask me any questions. Twitch.tv/DesoGames. Very easy to find. And DesoGames on Twitter as well. At Kirian Tech on Twitter as well. Kirian Technologies on YouTube, where you're watching now. Should be kind of easy to find us. And just follow us. Follow our progress. See how we're going to do this. See how we're going to change humanity forever. Thank you all so much. And until the next time.